Okay, welcome to Robotics 2. Today's class, we will do quaternions and then I will help you with the assignment. So what I want you to do is, first and foremost, go on to Canvas because this is very important. You're all gonna need it. There is this appendix d.rar. Please download and expand. So please download this appendix.rar and expand. There are 3 folders. Each folder shows you a different simulation, Simulink implementation of the MATLAB functions. So please open this and I will discuss this. Then if you have not done so already, UAV book main.zip are the skeletal files that we use to work on the project. So I want you to download this UAV book main desktop, and in there what you will see is these are the skeletal files for the projects. So since I have asked you to perform the Simulink part of it, you can do those same assignments using MATLAB or in Python. So click on the Simulink, and currently the assignment that we have given you is on chapter 3. Remember, this assignment is from chapter 3. Drag and drop it onto the desktop. So let me create new folder, and then I will drag my chapter 3 in here just to be safe. So now you will have your chapter 3, and in this chapter 3 you will notice that it will have this MAV dynamics, chapter 3, and state variables. Now it is important to note that for this code to run, you are going to need the files that you created as part of your previous project. So those files like draw aircraft and all those files need to be here. You will also need the parameters, because parameters are the UAV parameters that you are going to simulate. So you will need to grab parameters and place it in this file. So you will have this, and if you look at these parameters would have the Aerosonde parameters, which is nothing but the UAV that we want to simulate, which is like a flying wing aircraft. Then you are gonna need the tools. So basically that these tools could be anywhere. You can have it in parameters, and the reason for that is you have these Euler to quaternion and quaternion to Euler transformations that you will need if you are going to perform the integrations in quaternions. So I would recommend that make these changes. That way, when we start working on the problem, we kind of know how to solve it. So cut.
Is this the MavSim Simulink or MavSim MATLAB?
MavSim Simulink. You can do it with MavSim MATLAB, or you can do it with MavSim Python. That's totally fine. But I'm just gonna show that to you with MavSim Simulink. So before I begin, I want you to make sure that you have all these folders and files the way shown here, and then you have that appendix D, which is here, appendix D, and in appendix D you would have 3 folders: example 1, example 2, and the S function. So, and I'm going to explain it to you how you can create an S function that can take a MATLAB function or it can take a C code, and then how can you integrate and cross compile the codes, because that is needed for this project. Any questions before I begin? From my online students, from my in-person students? Any questions about the material that we discussed so far? Yeah, question? So let me finish the discussion on quaternions, and then we will derive the expressions, the equations. So bear with me for a second. Let me get this thing working. Office. Oh, they changed the chapter 3. Okay. So in last few classes, we talked about the kinematics equations for the UAV or the flying robot. And we looked at in the last class, the dynamics equation for the flying robot. Please understand, we have unfortunately, for some reason, the Zoom is not updating here. So okay. So there we go. In the last class, we talked about these 12 variables, and these 12 variables comprise of inertial positions, body velocities, body accelerations or angular velocities, and then the roll, pitch, and yaw. We looked at the translational kinematics that gives us the relationship between the inertial frame and the vehicle frame. We then looked at the rotational transformation that gives us the relationship between the body angular velocities and then calculation of roll, pitch, and yaw. So these are the important equations for kinematics. Please try to understand, these equations are fundamental equations that can be used for determination of attitude and position for or kinematics of any object. The only issue here is these equations are expressed in terms of Euler angles. They have singularity at 90-degree pitch. So in today's class, we are going to look at something called as the quaternion formulation. That means, how do we change these equations so that they do not suffer from a gimbal lock or 90-degree pitch singularity. And again, those equations are not difficult, but please understand Quaternion is a hyperplane. It's difficult for us to visualize. So even though we solve these equations in quaternions, when we try to visualize these equations, we convert those into Euler angles, because Euler angles are easier to plot or to visualize. Quaternions, even though they are elegant, they don't have singularity, computationally efficient, but they are difficult to visualize because we can only visualize things in 3 dimensions. This is something that we talked about in last 2 classes, differentiation of a vector with respect to frame. We also talked about the translational dynamics and how does it apply when you have a vector that is in the frame that is rotating. So you have a vector in the frame and the frame is rotating. And then that gives us these set of equations. They come from the Newton's law. Force is equal to mass times acceleration, or more accurately, force is equal to rate of change of linear momentum. If you extend these concepts further, if you take the rate of change of angular momentum, that equates to torque or the moment. So that expression gives you the relationship between the rate of change of angular momentum is equal to torque. Once again, this equation, the way I have written over here, is applicable only in 3 conditions, because angular momentum is always about an axis. Linear momentum is not. Linear momentum is on the axis. Angular momentum is about the axis. What that means is wherever you choose your axis, the value of angular momentum is going to be different, because angular momentum is the linear momentum multiplied by the radius. So wherever you have your axis, that radius term is going to change. So if you take angular momentum, or if you apply this equation around CG, this is the equation. If you apply this equation about a fixed point, that is the equation. But if you apply that equation at some random position, this equation will not be valid. And this is a very, very important point. And before I go further, I want this to be absolutely clear. So let me explain it to you what it means. Imagine that you have a pendulum. Okay, imagine you have a pendulum. And in robotics 1, we derived the equation for pendulum. We also numerically integrated the equation. Then we used Euler-Lagrangian formulation to derive the differential equations of pendulum. Remember that? And this is where the Euler-Lagrange approach shines. Now try to understand. We derived the expression for pendulum something like this. You have mass times gravity. You have the length of the pendulum. And then this is L. If this angle is theta, this is going to be L sine of theta. And then you get this equation, something like ML square theta double dot plus MGL sine theta is equal to 0. Remember, this is the equation that we applied. T is equal to I alpha. And at that point, I mean, when I discuss this, I kind of try to hint at it, but I want to make this point absolutely clear. This quantity is nothing but J, which is the mass moment of inertia. Okay, this is the mass multiplied by the radius of gyration square. Since this is the point mass, we just have one length. If I would have had a block, or if I would have had a rectangular block, then I need to consider the moment of inertia in 3 axes. This guy is the torque or moment. It is absolutely critical to understand that this equation, the way I have applied, is because I took the moments about this point O. So this is the moment, this is torque about O and is I about O. Everyone understands this? Because please understand, mass times the radius of gyration. Gyration means motion. So if I take my point O at this point, my radius of gyration is going to be L. Do you agree with me? This is M and the radius of gyration is going to be L. So this is about O. MgL sine theta, this torque quantity is about O. That's why T is equal to I alpha equation is valid. Everyone understood this? This is the usual way of solving. You can derive the exact same expression if you take moment about the CG. So this guy, this is CG. So what you can do is, this is CG. The only problem is, if you take moment about CG, you have to consider the reactions at the support. So for an example, if you are going to take moment about CG, then you will have to take into account, say, Ry and Rx. You have to take into account the reactions Mg. And you have to take into account these reactions. And please understand, the things are moving. So to find these reactions, you will have to apply Newton's law of force is equal to mass times acceleration. That will give you the values of these reactions. And then what you do is, you again apply T is equal to I alpha, and this is going to be CG. So you will say J theta double dot at CG plus. Now again, you are going to have torque at CG is equal to 0. Everyone understood this? If you start to work out this math, this doesn't come in one equation, because to find out Ry and Rx, you have to apply force is equal to mass times acceleration. Then when you actually take the moments, you have to take into account the moments of Ry and moments of Rx, and then finally that gives you the expression over here. But at the end of the day, the same expression pops up. There is another approach wherein, if you want and if you feel adventurous, you can take the moment at some arbitrary point over here. And this is, I'm going to call this point P. But if I take moment about point P, this equation is incorrect. This is not right. This equation is not correct. And you will have to add one more term, which is actually considered as MAD. MA is mass times acceleration multiplied by the distance. And this terms comes in the picture because, let me tell you what is the physical interpretation of this. Imagine here we did not have this term. MAD term did not exist. MAD term does not exist. This term is nothing but moment of linear momentum. So basically, this is, if you think about it, force times acceleration, mass times acceleration is give you force multiplied by distance, that gives you torque, and these terms match. This term, MAD term, is not present when you take moment about the fixed point or you take moment about the CG. So that's why this is not preferred. So whenever we studied in robotics 1, or as a matter of fact, when we are going to study robotics 2, we are by choice going to apply our equations at CG, because we may not have a fixed point. That aircraft is flying, that aircraft does not have a fixed point. This pendulum has, so we can use this frame of reference. But for aircraft, we are going to use the moment about CG. You can use an arbitrary point and apply this again equation, but do not forget this additional term that is coming in the picture, because now the moment is not about CG or at fixed point. Everyone understood this? That is extremely important. And unfortunately, this is not emphasized when we study undergraduate dynamics or even graduate dynamics. But please try to understand this point is very, very important. You cannot arbitrarily apply T is equal to I alpha. Okay. Now, next part is, this is the rotational dynamics. Our aircraft is a three-dimensional object. So what we need to do is, we need to extend this logic. I want you to understand, I have a mass multiplied by the radius of gyration. This is in one plane. There is only one length. Now imagine, instead of a point mass, you have a big blob where the mass is distributed. So if you take teeny tiny amount of mass that is distributed, its X, Y, and Z position is going to be different. Which means what we need to do is, we need to perform the integration. But at the end of the day, I want you to look at first term. Dm is the teeny tiny mass, and what you have is y square plus z square. Pythagorean theorem is the radius. So what you have is, you have those radii along the diagonal terms, and then you integrate. Now the problem is, if it's a symmetric object, that's good. But when the object is not symmetric, realize that the mass distribution on one side will be different than the mass distribution on the other side. So what happens is, when you are looking at the sort of the radius of gyration around the cross terms, you get x times y, x times z, and all those terms. That is because the mass distribution is not symmetric. If the mass distribution is symmetric, which means if that object has axis of symmetry, then those off diagonal terms will vanish around that axis, around those axes of symmetry. Everyone understood this? And this is extremely important because some of you are not from mechanical background and might have not studied the dynamics in detail. But at the end of the day, all three-dimensional dynamics comes to this equation, wherein you apply the equations at CG, or you apply the equation at fixed point. Since the aircraft is moving, we cannot apply it at fixed point. Since robots are moving, we cannot apply it at fixed point. So we always apply it at CG to make our life easy. So we apply the equations at CG, and now what we have is, we have the rate of change of magnitude of the angular momentum plus rate of change of direction of angular momentum, which is cross product between the angular velocity of the frame and the vector itself. And then that is equal to the external torques. Everyone understood this? And then what happens is, you have this inertia matrix. And then please understand the aircraft is like a cylinder with wings. So the axis of symmetry is IB and KB. So basically in that plane, the aircraft is symmetric. So you got zeros as the off diagonal terms. You find the J inverse, which is the inverse of the J matrix. And then in the last class, I spent some time on performing cross product when you have a row vector and cross product when you have a column vector. So this is nothing but again same thing as what I have shown on the top, except now those vectors are represented not as row vectors but as column vectors. The order of multiplication is very important. That's why I have components of A along in the matrix and components of B as vectors, because the cross product is from A cross B. That's why terms in A go in that 3 by 3 matrix and term in the B are in that 3 by 1 vector. Everyone understood this? And then it's just matter of substitution. You can substitute all those values here, perform the matrix multiplication, and you get this scary looking equation. Okay. This equation, along with the previous equation, defines the motion of any flying robot. As a matter of fact, any flying object. Remember, there are 6 equations describing 3 positions, 3 angular velocities. And then there are 6 equations that are describing the dynamics. So you have kinematics equation, which gives you the position relationship, kinematics equation that gives you angular velocity relationship. You have force is equal to mass times acceleration, and T is equal to I times alpha. So now you have 12 equations. Everyone understood this? And the basic purpose of the project or the assignment is take these equations, program them inside the MATLAB, numerically simulate those equations. Once you numerically solve those equations, you are gonna get solutions to Pn, Pe, Pd, U, V, W, P, theta, psi, and P, Q, and R. Everyone understood this? And then feed those to the aircraft simulation model that you have created, draw aircraft. Everyone understood this? The only small change here is I want you to understand on the right hand side of this equation, we have forces Fx, Fy, and Fz, and the torques, which are M, N, and Q. So there are forces and there are torques that are acting. So M, L, M, N, L, M, and N. So these are the torque about X, torque about Y, torque about Z. So basically, on that aircraft, we have 3 external forces, Fx, Fy, Fz, and 3 external torque, L, M, N, about its body axis, body X, body Y, body Z. Everyone understood this? So what we are going to do is, in the simulation, we are going to input those forces and torques and see how does the aircraft fly. In this assignment, we are just going to feed those values numerically. I mean, we will just hardcode the value. We'll just substitute some random values. When we study the next chapter, which is the chapter on forces and moments, we will actually find out Fx, Fy, Fz, and L, M, and N, depending upon the airfoil geometry, depending upon the propeller thrust, depending upon the deflection of the control surfaces, and so on and so forth. So in today's class, once we are done with it, we will have an aircraft that is flying where we are supplying the forces. After discussing the next chapter, we will write a MATLAB code that will calculate the aircraft forces depending upon the flight regime and then feed that to the simulation that we have. And subsequently, as you go further and further, you will improve the fidelity, you would add the wind model, you would add the altitude model, you would add the temperature effects, density variations, all that stuff, and you'll actually have a nice flying simulator. So basically the aircraft simulator. Yeah.
Are these values in correlation with other values?
Yeah. So whenever what I will do is I will try to give you some physical meaning for those values. For example, what happens if you add if you want to just do a Dutch roll, or what you want to do a complex maneuver. So at this point, we will supply some values and see if our simulation behaves the way we want it to behave. That is absolutely very important, and that is part of your assignment. That supply some values and make sure that the simulation is working the way it is expected to be working. By the way, the working solution of this problem, just the solution, not the simulating file, how your aircraft should behave, the solution is posted on the book website, Solution to Project 3. There is a YouTube video where the author shows that how would, if you change certain value of force, how the aircraft should perform. So before you turn in your assignments, make sure that you are able to do those maneuvers and your results are exactly same as what are shown by that author. However, there is little twist. These equations are implemented in Euler angles, which means if you take these equations and try to simulate an F-16 or an aircraft that can do 90-degree pitch, or an aircraft that is doing a nosedive, that system will not work. So what I will do is, after we are done discussing the Newtonians, I will show you how these equations can be modified so that you can avoid gimbal loss. And that is what you should focus. Then that simulation can be used for any aircraft, missile, or anything which can do 90-degree pitch. Everyone understood this? And I want you, if you have not done it, not in the class, but I want you to go to 3 blue 1 brown. And watch the 4-part series on Newtonians. So if you go to the website 3 blue 1 brown, Grant, he is an expert in making super complicated topics super easy using cartoons and animation. So he has a 4-part series on Newtonians. He also has a series on machine learning, data science, linear algebra. But I want you to watch this series on Newtonians. That will give you a physical interpretation of what Newtonians are. Okay, moving on. In the last class, I gave you a basic explanation of Newtonian. Newtonian is like you have an axis, you have the rotation about axis. So axis angle representation is Newtonian. But as soon as you are going to define axis, you are going to need I, J, and K's. And if you want to define rotation, you are going to need additional theta. So Newtonian has 4 elements. And those 4 elements are E0, E1, E2, and E3. The important part of the Newtonian is Newtonian's integration can diverge. So at every point of time, if you say it's a Newtonian, we need to normalize. What do I mean by normalization? Normalization is something similar to finding the unit vector. So if you are given a vector, so for an example, if you are given a vector, which is 5i plus 3j. And if I say this is the unit vector P, and I say I want to find out the unit vector in this direction, this is going to be 5i plus 3j divided by square root of 5 square plus 3 square divided by square root of 5 square plus 3 square, so that this guy becomes a unit vector. This is a vector. So similarly, you have a quaternion E0, E1, E2, and E3 at every time step. Before you do anything, this quaternion must be normalized. So what you do is you divide everything by the magnitude of E0 square plus E1 square plus E2 square plus E3 square. So quaternion or the modulus, the magnitude of the quaternion needs to be 1. Remember this, you can't just take arbitrary quaternion and use that to calculate angles. Before you do anything on quaternion, at every time step, you have to normalize. Now, we just gave you a intuitive definition, but quaternion can represent multiple rotations. So for an example, if you have a roll, pitch, and yaw rotation combined together, that big direction cosine matrix, combination of first rotation matrix multiplied by second rotation matrix multiplied by third rotation matrix, that whole big matrix can just be represented with a quaternion about an appropriate axis. And that is the beauty of quaternion, which means if you want to propagate the rotation, if you want to propagate a direction cosine matrix, you will have to keep track of 9 elements. But if you are going to propagate quaternions, you just have to keep track of 4 elements. And that may not seem like a big saving, but when you are performing the flight calculations 1,000 times a second, every calculation saves a lot of time. Over the time, quaternion multiplication is more efficient.
With the way quaternions are structured, is it possible if there's 2 different quaternions that use the same orientation?
Same different quaternion with the same orientation. I'm gonna say answer is yes, but I think the answer is yes, but yeah, axis angle changes. So what I want to do is I want to show you, and again, you don't have to remember all these equations. MATLAB has built-in functions, or remember the tools folder that we copied onto our Simulink folder that has this code written. The only thing what I want you to understand is, if you are solving in terms of Euler angles, it is possible to construct the quaternion from Euler angles. So input is roll, pitch, and yaw, and it will give you a quaternion. So E0, E1, E2, E3, it will give you a quaternion. Alternatively, if you have a quaternion, you can perform that conversion and you can get Euler angles. So conversion from quaternion to Euler angles to quaternion is possible.
I think at least when I downloaded the tools, the Euler to quaternion function blank, like I think they went in the built-in. Can I use the built-in?
You can use the built-in.
And then the grader set takes pictures. Does he want pictures of these formulas? Or can I just show a picture of the built-in?
Where is the grader?
He listed their stuff for the assignment of like building a PDF and showing.
Yeah, he's listening to the lecture on Canvas. I mean, listening on a Zoom. Send him a
So
question.
if we can use the Euler.
I am totally okay with it, as long as your answers, basically the function here that are written. So aerospace tool, if some of, basically they wrote the whole function because if you don't have access to aerospace toolbox, you don't have access to those functions. But fortunately, we have access to all the toolboxes. Okay, so this is what, if you are working in quaternions, and then if you want to explicitly capture the rotation matrix, this is the multiplication. So what if I give you a unit quaternion, and if you want to sort of see what does that unit quaternion represent in terms of rotation matrix, then you can perform this and that gives you the rotation matrix. Now, I don't know if you understand how powerful this is. Imagine there are 10 rotations, like the rotation about the first frame, second frame, third frame, fourth frame, fifth frame, sixth frame, seventh frame, eighth frame, ninth frame. The whole thing, 0R7, 0R7 can be represented with just one quaternion. But for some reason, if you want to capture that 0R7, just plug that quaternion in here and you will get 0R7 as a matrix. So you don't have to keep track of all those frames. So quaternion, they are computationally very, very powerful. Now, if I were to use, this is the most important slide you need to understand for your project. If I want to use the quaternion implementation, remember earlier we had 12 equations, but since quaternion are 4 elements, not 3 elements, now I get 13 equations. And these equations are, let me be very, very clear. The first 3 equations, you had a direction cosine matrix that was sitting in there. Do you agree with me? Cosine P, sine theta, all those values. So what I did, I replaced that matrix. And I will show it to you here. So what happened is these are your original equations. These are your original equations. Do you agree with me? What you see there is sine theta, cosine phi, and all those terms which are expressed in terms of Euler angles. I'm going to take that quaternion expression and replace this direction cosine matrix by that quaternion representation. Everyone understood this? So this guy will be replaced with this guy. Do you agree with me? And then again, you have this guy, because please understand, we don't want Euler angles. I don't want phi, theta, and psi. Instead, I want E0, E1, E2, and E3. I would replace that with this guy. Are you with me so far? But when I did that, initially I had just 3 variables, roll dot, fish dot, yaw dot. Now I have the dots on E0, E1, E2, and E3. So I need to track the derivative of the components of quaternion. Everyone understood this? However, there is a big advantage here. Earlier, there were all sine and cosine and those types of terms. Do you agree with me? Those functions are non-linear. But as soon as I do a quaternion representation, can you see that the whole thing became linear? Which means if you were to perform these computations, hey, grader is here. You can ask him questions. No one.
You said it's okay
After
to
class.
use the building.
So basically, what has happened is those equations, nonlinear equations, became linear. The only cost here is we have to add one more equation, because earlier we had 12 equations. Now we have 13 equations. Everyone understood this? So in next half an hour, what we are going to do is we are going to take these equations and create a MATLAB S function that can integrate the quaternions. But here is the problem. The biggest problem with quaternion is they grow. And as soon as they grow, at every step, it's no longer a unit vector or unit quaternion. So at every integration step, you have to normalize before you feed that information to the next integration step. Everyone understood this? There are multiple ways of doing this. One simple way is once you integrate at the next step, whatever results you get, you normalize, and then you basically go to the next step. The other approach, which is a little bit smarter, is basically you add something called as the normalization steps, which means you have this first part is the integration minus lambda partial j by partial e. So we are taking the partial derivative of the cost function with respect to the Coulombian. And then once you expand all that, and this is actually super simple to implement the code. What you need to do is this equation will get appended by this term. You will have lambda in the parentheses 1 minus E0 square, E1 plus E1 square plus E2 square plus E3 square root. And that term will get repeated around the diagonal where there are zeros. You choose the value of lambda, say 1000 or 100, and basically at every integration step, your Coulombians will be normalized. So there are two steps. Find the solution, add one more step, and in that step, you normalize it before the next iteration happens. Or what you do is you add a constraint so that the Coulombians, the integration itself, are normalized. And this may look complicated, but this is super simple when I implement it. Everyone understood this? Okay. And I will walk you through this code. I will also show you how the code should work. I will also show you the solution, and everything is recorded. So you can, if you need something, you can go back and refer to the code. These are some few steps on the Runge-Kutta integration. Runge-Kutta integration is like the numerical integration. First numerical integration is Euler integration. Then you add trapezoidal rule. Then you add parabolic, and then you can improve the accuracy of integration. So these are the different, if you have taken any course in numerical analysis, you must have studied these in detail. EGR 217 or 219, you must have studied this in detail. Now let me talk about the project in hand. So in this project, implement the miniature air vehicle equations of motion given in equation 3.14 to 3.17. Those are either 12 or 13 equations that we talked about. Take those equations. Assume that inputs to the function are just arbitrary forces and moments. We have three forces, Fx, Fy, Fz. We have three moments, L, M, and N. So we are feeding those to that function. And then changeable parameters should be include mass, the moments, and products of inertia. So you are free to use whatever value of J that you want. But for consistency, there is a UAV called Aerosonde. That is the UAV, the J parameters for that UAV are given. So I would just use the inertia parameters for that UAV. And then it's saying that use the parameter given in appendix E, that is where the Aerosonde parameters are given. Verify that the equations of motions are correct individually by setting the forces and moments along the each axis to a non-zero value and convincing the motion is appropriate. For example, if there are no forces, no moments, aircraft should stay stationary. It's like a static equilibrium. If you just apply f of x, then the aircraft should go forward. If you just apply the roll moment, it should actually just keep on turning. So you have to make sure that the aircraft simulation behaves what our intuition says. And then the last part is you have a gyroscopic coupling. So this is something that I want you to understand. Aircraft, they do not take turn like this. So imagine okay, let me show you what I mean. So if I have an aircraft, let me get my 3D printed aircraft. Okay. If this is the aircraft, if you want aircraft to turn, aircraft will not turn like this. So aircraft going forward, it cannot turn like this. This is not possible for the aircraft. The only way aircraft could turn is something like this. So that is called as banking. Why does aircraft have to bank? Aircraft has to bank because of the gyroscopic coupling. There is a coupling between the roll and yaw. Aircraft cannot yaw like this. If aircraft needs to turn, it has to roll and then turn. Everyone understood this? Yeah.
Only rudder won't make it yaw.
Even so, rudder is supposed to make it yaw. But what happens is when the aircraft starts yawing, because of the coupling, it tilts.
Under actuated system.
Under actually
It has, how is a roll and a super
dynamical equations of motion. If you look at the dynamical equation of motion, easiest way to show that to you is we will run that in simulation. Yeah.
And part is because the rudder is above the center of gravity, so when you exert force there, it twists the entire body.
So basically, for this aircraft, there is no rudder. Rudder means and again, in the next class, we'll talk about the different aircraft configuration. Some aircrafts, they have rudder, some aircraft do not have rudder, some aircrafts have ailerons, some do not have ailerons, some have elevators, do not have elevators. But at the end of the day, dynamics is the same. No matter what you do on those control surfaces, those control surfaces are going to generate f of x, f of y, f of z, L, M, and N. And those three forces and three moments get applied to the equations of motion. Yeah.
I'm just curious, since rudder is used for moving left or right, how does this one move?
Yeah, forces and moments. Because there are basically what you have is you have at the back. This is something like aerosonde. So this is the aircraft, and what you have is you have flaps like these. And what happens is you can move the flaps together, or you can move the flap opposite, and that gives you the actuation. So there is no rudder, but you have flaps. So and they basically they can move in one direction, so the aircraft can go up. They can move in other direction, the aircraft can go down. They can move opposite to each other. It will rotate in one direction. It will turn in other direction. It will rotate in other direction. So basically, differential movement. Yeah, but and there are some crazy planes. You will see that they arrange and to turn the flying aircraft, it does not require a lot of motion. I mean, if you are on if you are flying and if you get a window seat, if you look at those flaps, you will notice when aircraft is turning, the movement of those flaps is very, very small. Because even though the motion is small, the cumulative effect on the boundary layer and aerodynamic forces is huge. That makes that aircraft turn. Okay. Next part is I'm gonna talk about the S functions. Any questions from my online students? Or in-person students? So what I want to do is, first and foremost, and this is not a spectator sport. So please open MATLAB and please open Appendix D, folder number 1, and open this S function. So what I want you to do is, I want you to go to Appendix D. I want you to go to example 1, and in this example 1, you will notice there is something called as the second order, which is the Simulink model, and second order .m. Now, if you look at if you open the second order Simulink model, you will realize this is a very, very simple model wherein that S function is the ordinary differential equation describing the dynamics of spring mass damper system. So if you look at the spring mass damper system, the equation of motion is x double dot plus 2 omega n x dot plus omega n square x is equal to some external f of t. And we spent a lot of time in robotics 1 dissecting this expression. We looked at the eigenvalue, stability, all that stuff. At the end, if I want to solve this expression inside MATLAB, what is the first step? If I want to use OD45, OD123, what is the first step I need to do?
Define symbols.
Symbols, convert that equation into a first order differential equation. Remember, into state space form. So in the state space form, I know you know this, but for my own satisfaction, I will have to write this expression something like x dot plus 0 f of t and x derivative of x is nothing but x dot omega n square minus 2 omega n. Everyone understood this? Before you do anything, this is what you need to do. Is it coming back? Okay. So what we are going to do is the S function that is shown over here, second order, would comprise the code that actually defines this equation. So here is how you should do it. And I want you everyone to pay attention. First and foremost, Appendix D, example 1. Can you see S function template? S function template. Open that. If you want to create an S function, this is the template that MATLAB has provided. You want to modify this template as per your requirements. And there is good discussion on this in Appendix D of the textbook. So if you read that Appendix D, it will tell you line by line how it is implemented. But the idea is, this is the S function template, and you can take an ordinary differential equation, put this in the template, and then use that ordinary differential equation inside the Simulink. So this is the S function template. The general form of the template is something like this. And to be honest with you, it doesn't have to be this complicated. You can actually write your own templates, but for the first implementation, my recommendation to you is just follow this template. And then what needs to happen is this template is given to you. There is initialization, there is derivative, there is system and optional parameters and all this stuff. The only thing that you need to modify is something over here. So can you see this? If I want, okay, let me discuss this. So these are the different flags, that standard flags that MATLAB uses. Then you can do it continuous or discrete. Then it will ask you for number of inputs, number of outputs. And then basically, if you want to find the roots, feed through, some sample times, all that stuff, offset time. And so these are the flags. And then if you want to modify, what you need to do is you just need to modify a few lines of code in this template that will have. So basically, so these lines you have to modify. So what is the output of the function? What is the update? And then basically your equation, this is MDL derivatives. Now what I want you to do is, everyone open this template, and I want you to open second order underscore m.m. And please note that the exact same template is used to program this equation. So if you go down, first remains the same, second remains the same, everything, please understand here. Your inputs are, this is where the function is. MDL derivatives, the input to that function is the time, initial condition, U, which is the external force, value of zeta, and value of omega n. In this particular equation, this is external force that we have to supply. Value of omega n, value of zeta is given to us. So for that particular system. And then you have to supply the initial conditions for numerical integration. So what has happened is you have defined the function here. Now you need to get some outputs. What outputs you want to take? You want the outputs like time, x, u, omega n. So basically you define these outputs. And then please understand the numerical constant, omega n and zeta, they are numerical constant. So how many numerical constants do we have? 2. Then how many inputs do we have? Just one external input, u of t, so 1. How many outputs do we have? Just 1. So we have one output. And this sample time is always by default 1 because you are doing the continuous system. Then you define the initial conditions. I'm saying my initial conditions are zeros. Then str, you have to keep it as is, continuous sample time. And I want you to look at, this is where that code is implemented. This guy is here. The only thing is they flip. x2 dot is equal to x1 and x1 dot is equal to 2 zeta omega and x1 omega n square x2 plus e. Everyone understood this? At least can you see that the equation that I have written here is similar to the equation that I have there? And then in the outputs, you have omega n square x2. So which is nothing but it's finding the velocity, omega n square x2, that is the output. Now what you should do is, you should go to Simulink and you will supply a sinusoidal input. This sinusoidal input is plotted onto this scope block, and this is the function, second order function. And can you see, this is where I'm specifying the name of that MATLAB file, second underscore order underscore m is where all that Simulink function code is. Everyone understood this? S function parameters are the constants that I'm classing to that parameter. So omega is 10, zeta is 2.5. You can hard code it. That's totally fine. You can put it in the code and you don't have to supply anything over here. And now what I want you to do is, I want you to click run. And then you will realize that I get the solution over here. So what I have done is I have created a MATLAB code, encapsulate that inside the S function, and then use that S function in the Simulink. There is another way of doing it. Is imagine that you already have a C code, and what you want to do is you want to take that C code and convert that into S function. So for an example, if you have this C code, and this is very, very useful because what you can do is you can have a C code that is running on embedded system, use that C code, put it inside the MATLAB, wrap it around the S function, so you can simulate how that embedded system would behave, and the code snippets remain the same. So you know how it will behave in the MATLAB environment. You can make modifications. You can add some MATLAB toolboxes, some MATLAB signal processing, and then get the results that we are looking for. Everyone understood this? I'm not going to explain this, but this is given in the textbook very nicely. Now let's talk about the problem at hand. So in this new folder, chapter 3, what I want you to do is, I want you to open first and foremost this MavSim chapter 3. When you look at this MavSim chapter 3, this MavSim chapter 3 toolbox, the template is going to give you something like this. At this time, please understand your draw aircraft should have been complete. You should have the code that does drawing of the aircraft. Now, what we need to do is, between the forces on the left, can you see Fx, Fy, Fz, L, M, N? Between the forces on the torques on the left, we need to add this dynamics equation that is numerically integrating the equations of motions that we talked about. Everyone understood this? Now, what I want you to do is, I want you to double click this, and you will see that the name of this parameter, S function name is MAV underscore dynamics, and S function parameters is MAV. Those MAV parameters are corresponding to micro air vehicle parameters that are used for computation of inertia parameters. So if you look at this S function parameters, MAV is where all the J values are stored. Okay. Any question about this Simulink code? Now let's focus on how this MAV dynamics thing is written. So if you go to the second line of code, MAV dynamics, double click on that. And now what you have is, you have this MAV dynamics code. Please note, this follows the exact same template of S function. You agree with me? This follows the exact same template of the S function. However, you have case 0, case 1, then you have update case 2, case 3, case 4, case 5, 9. You don't have to change anything here. The thing that you need to change here is, please try to understand that MAV file has 13 parameters corresponding to the J values. So you have 13 parameters. Your states are 12. So it's outputting 12 states. You are applying 3 forces and 3 moments. So can you see the inputs are 6 and sample time is 1. And then when you go down, this is where your initial conditions come in. We are going to work in quaternions. So we have a north velocity, initial velocity. We have east velocity, initial velocity, down velocity, body velocity, u, v, w, initial at time t is equal to 0. And I have quaternions E0, E1, E2, and E3. Everyone understood this? These are the quaternions. And finally, I have P, Q, and R. Those are the angular velocities, initial values. Now then I will have to do the initialization, simplification, and here it defines all the states. So for an example, Pn1 is x1, Pn Pe is x2, all the way down here. You can go through it, and this is where you need to fill in the blanks. Pn dot is equal to what? Remember those 13 equations that we talked about? Those 13 equations you have to type in here. This is the first equation, second equation, third equation, fourth, fifth, sixth, 7, 8, 9, and then you will get these 12 equations. And finally, you will send an output here, and you do not have to change anything else over here, except you will have to send these outputs, and then this would remain as is. Yes.
So when we translate the equations there, we're really gonna pull the equation, we don't need to translate that into space or anything. For those equations, the equation provides that slide. And all those variables. for self-
Are you ready? Take a picture. I'm going to show you the equations. You don't have to because I'm recording. So everyone understood what needs to happen. Looks complicated, but it's not. Okay. Why are we saying something? What is the use of it? Because we can wrap anything inside the S function. We can write the MATLAB code. We can write a C code. You can use a Python code and wrap it. Okay. So now what I'm going to do is I'm going to show you how the solution would look. So first and foremost, everyone is good with the draw aircraft. You guys got the aircraft drawn correctly. Okay. So, let me see. Chapter 3, this is, yeah. So chapter 3. Oh, yeah, because there is already a Simulink file. So I need to close all this. So please understand, this is the same solution. And once you implement everything correctly, when you run it, what you should see is you should see these values. These are the aircraft values, and you should see your aircraft. Now, if you change this value to 0, if you change this torque to 0, you will notice in the simulation. Let me stop this and then run. Everything is 0, run. And you will see the aircraft is in static equilibrium. What you are seeing there is you are seeing P, Pn, Pd, Pe, Ph. You are looking at the roll pitch yaw, and then you are looking at PQR. So you can see the aircraft is kind of flying in a level flight. Here, if you increase, maybe if you increase the torque. So let me see if I give it some amount of torque. So you will see this aircraft starts turning and yawing. So let me give some value of torque, and you will see this aircraft. So you can change these values, and then you will see the aircraft maneuvers. The aircraft is changing, and you should do something similar. Now let me show you. Yeah, it will do the dust roll and all. It will show you all the things. Now here is the most important part. I'm using Aerosonde parameters.m. And if you look at Aerosonde parameters, it will actually initialize all these quaternions. It will also give you mav.gravity, mav.mass, mav.jx, this structure that gives you all these parameters for Aerosonde. And then once you go to mavdynamics.m, this is the same code. First line is same as the template. All the way it is same. What you need to do is you need to program these equations in here. And I'll show you the equations. So you have to add this R matrix. Remember what's that R matrix? It is the rotation transformation, converting quaternion into rotation matrix. I showed that on the slide. Did I tell you there is a mistake that I want you to fix it? I'm just kidding, there's no mistake. Then you have P dot, because what you need to do is you are getting all these velocities U, V, and W are in body coordinates. those need to get converted into the inertial frame. So that is where this guy is. And then these are the next three set of equations. Can you see that? Can you see that 1 dot MAV dot mass, 1 dot MAV dot mass? These are the same equations that I talked about. Yeah, take a picture. Everyone got a picture? Now this lambda value is that optimization parameter for the cost function, because we want to normalize the Coutonian at every step. That's why you need to supply some value of lambda so that Coutonians can automatically be normalized. And this is that matrix. Can you see? Can you see W, this value minus P, Q, R, P, lambda, 1 minus normal R, P, Q, R. And finally, this is where you are propagating the Coutonian. Okay, does anyone else need to take a picture? Then you have these Coutonians. Then finally, what you do is again P dot, Q dot, and R dot. These are the equations. And when you pass it on to the system, you see here. And I'm gonna stop here, but I haven't showed you one important part of the code that I want you to figure out. So after this, what you need to do is you need to send the output, correct output. Only then the code is going to work. This is not going to work. You have to actually package the output correctly so that it can feed into your code. And I will let you figure that out. But that's it for today. Does anyone want to take a look at the code again? No?
I think the corresponding coefficient are slightly different.
Yes. Yeah, actually use this. These are better. Okay, any